You said you've never been melted before. Your heart's never really dripped on the floor. You don't think that I could make you liquid?
Change of variables. So change of variables. So far, we have seen a change of variables from rectangular to polar. So I'll do a little quick list here. So far we've done rectangular to polar, rectangular to polar, which is from x, y to r theta. We've also done rectangular, I'll abbreviate, rectangular to cylindrical. This is kind of just like the 3D version of polar, you can consider. So x, y, z goes to r theta z. So z stays the same. It's represented the same in rectangular and cylindrical. And finally, we went from rectangular to spherical. And this is where the interesting, or the more exciting variables come in. And this is also three-dimensional. So this is our rho, phi, and theta. Okay? So these are the three categories of change of variables that we've been doing so far. And these are all types of change of variables. And now we'll just kind of generalize it to a more general formula. So for the first case, this is mapping, it's called maps R2, so the plane, like XY plane, to R2. So we're saying we're going from one plane to another. So this is a two-dimensional plane, that's what that represents. R3, if you were to have that's your XYZ axis, that's three-dimensional space. But here we're working in two-dimensional space, so in effect, this is what we're doing. We have some plane, let's define it with the axes u and v, okay? And in this space, or in this plane, we have a domain, and we'll call it d naught, all right? So this is our domain in the uv plane. And then we want to map this, so we want to take any point in here and do something to it. Okay, so that it ends up in a different plane. So for example, x and y. Okay, so now what we're doing is we're taking this point here, let's say, so g, some function of u and v. So some function takes a point from the uv plane, some point in the domain, maps it all the way over here into, let's say, another point, right? But now this is an xy point. Okay, so we're taking g of uv. So this function g, the input is a point from here, and then it takes that point and transforms it into some kind of xy, some point with xy coordinates. And this x and y depend both on u and v. Okay, so this in effect is what that's doing. This is called a change of variables. Okay, so then anyways, when you take a collection of points and you transfer them over here, you're going to get some other kind of domain, all right? So this is going to be our normal D, no subscript here. Okay, so this is our change of variables, again, just to clarify, is from UV into XY, all right? So it takes points in D, I'll just write it out here, takes points in D naught and maps them, that's the special term for it, and maps them to points in D, to points in D, okay? So that's what, in effect, that's what it's doing. And now let's explore this mapping, I guess you could call it, more mathematically. So now what we're interested in is the double integral over these domains, right? Because that's what we're concerned with in this course, is mainly about integration. So when we have the double integral of over D, so this is the second one, it has to do with x and y. So we have our normal f of xy dx dy. So we want to find out what is this in terms of u and v, all right? So this is like the right side, the right graph that I drew on the last slide. And so now x we can think of as in terms of u and v, remember? And y is now the same thing. It's determined by u and v. That's a function of u and v. And then we have to figure out our dA. So our dx dy, that's the same thing as dA, right? So remember, I'm just going to go back a little bit and talk about polar coordinates and spherical coordinates, and cylindrical for that matter. Whenever we had a change of variables, remember how we had our dA for polar was dr d theta and the r in front. Remember, this was the factor that the differential area changed by. And likewise with dv, with spherical, it was rho squared sine phi d rho d phi d theta. And this was the factor that it changed by. So now we need to know what is this factor in front here so that we can have our du and dv. There is going to be something here. It can't just be one. Well, in some particular cases it can be, but we need to find a general form for it. So to find this area change, basically, so the area change incurred when you map something. So area change under a mapping, that's what that's called, mapping. From D naught to D, because that's what we're doing in effect. We're moving from UV to XY, so we want to represent this integral in terms of UV. So we're kind of going backwards a little bit. So this corresponds to U and V, and this corresponds to X and Y. Okay, so we're going this way and trying to get it back in terms of U and V. So this area change is given by a factor calculated technically as it's called the Jacobian determinant. Okay, so and actually the absolute value of that's also important. So what we have, I'll explain on the next slide what the Jacobian is. So that's just its abbreviation, is Jacobian, because not everybody wants to say Jacobian determinant. Take the Jacobian determinant. Anyways, so what we would have, let's say, so we have our g of uv, right? This is the function which maps uv points. It sends them into the xy plane. So then we have our x and y over here, which are both functions of u and v. Okay, so this is our equation. And from here, to calculate the Jacobian, this is the formula. This is the process you would follow. So the Jacobian of g equals, and now we're going to have big signs here. So we're going to have the partial of x with respect to u, and below it the partial of x with respect to v. Next to it, next to the top one, the partial of y, partial u, and partial y, partial v. And then to calculate from this matrix here, we take the first diagonal going down, so this one right here, and we multiply these terms. So we'll get d partial x, partial u, times partial y, partial v. And then we subtract, this is just inherent in the formula, minus the other diagonal, the product of the diagonal. So then it will be minus dx dv times partial y, partial u. And again, we're taking the absolute value, so we have to have our absolute value signs. Okay, so that's basically it. This is what fills in that blank spot, the Jacobian. So what we'll have is Jacobian. This is the Jacobian. Okay, and then we would multiply this times du dv to get our area, our differential area. Okay, and then just a side note, Jacobian is also abbreviated. You might see this as well. It's denoted by partial of xy over partial of uv. Okay, that's just another way of writing this. Those are just the same. Okay? Alright, so now on the next one, I'll write out what our full formula would look like. So if we're trying to calculate the double integral over d of f of x comma y dx dy, this is going to equal, and then we have the double integral, and now we're switching into uv, so the big change of variables happening here is going from xy back to uv. Okay, so here we started off in domain D, but now u and v correspond to d naught, d subscript naught. So we'll be integrating over d naught, because now we're switching into u and v, and this is going to turn out to be, so now for x and y, we plug in our x, which now depends on u and v, and our y, which depends on u and v. Okay, and then we have the differential area, dA, which is now represented by the Jacobian with partial of x comma y over the partial of u comma v. So that's our the area factor. Remember, that's how much the area changes when you switch variables. And then just our du dv, or dv du, whichever way you want to write it. Okay, so that's the formula in a nutshell. Okay, so yeah, let's get started on an example. We'll practice computing the Jacobian. So for this one, we're going to compute Jacobian. Okay, and the function that we're given, the g is of r and theta, equals x of r comma theta and y r comma theta. All right, so we have to compute the Jacobian of this mapping function. So we're not really given anything other than this, but we are supposed to use our prior knowledge that x is r cosine theta and y is equal to r sine theta. Okay, so here we have, see how this, I could technically rewrite this as x of r and theta, right, because it's a function which depends on r and theta, and this is the same thing as y of r and theta. Okay, so let's say I wanted to, well, let's just get started computing the Jacobian right away. We can do, well, okay, let me go back. I'll do a little simple drawing here so that you guys get some more insight as to what we're doing. So we have, right now we're in r and theta. See, we're taking these points here. So let's say we have some kind of d naught, right? This is where we're starting. We're taking points from here and sending them into the xy plane. So then we have x and y. So then we have some other shape created here, and this is our domain D. And it just so happens that we have another function, capital G, of r and theta, which allows us to map points from r and theta plane to r and theta to x and y. And G allows us to do that. Okay? So anyways, getting back to the Jacobian. So we have Jacobian of G. We're going to take the absolute value of it. Okay, so this is equal to, let's rewrite the formula again so we're more familiar with it. Partial of x over partial of u, well, okay, not u in this case. On the bottom, now we're going to have the first variable that it depends on, so partial of r. And then down here, we still have the same thing, partial of x, but this time it's over partial theta, okay? And then we're going to do the same thing over here, but this time with the y. So partial y, partial r, partial y, partial theta. Okay, moving on. So now let's plug in what we get. So partial x, partial r. So that means differentiating this function here with respect to r. So we're holding theta constant. So with respect to r, that would be cosine theta, goes here. And then partial x, partial theta. Now we're looking at theta. We are differentiating with respect to theta, so we're keeping r constant. So that means that we're going to get a negative r sine theta. Okay. Now let's do the y ones. Now we're looking here. And if we differentiate with respect to r only, then we'll get sine theta. And the last one, dy, partial y, partial theta, that's going to be a positive r cosine theta. There we go. Okay, so keep this in mind, jot that down, and I'll move on to the next step. Okay, so we're going to take the, well, I guess I'll just write it here anyways. Okay, I'll rewrite it, cosine theta, and then we have a negative r sine theta down here, positive sine theta up here, and a positive r cosine theta. So this is our matrix C, I guess you could call it. And first we have to take the product of the first diagonal. Okay, so this will be r cosine squared theta, and then subtract the product of the other diagonal. Subtract this thing. So then we'll have a negative r sine squared theta. So this these two negatives turn into pluses, and we get r cosine squared theta plus r sine squared theta. And we can factor out an r easily and get r times cosine squared theta plus sine squared theta. And again, here's the useful identity that everything in parentheses here equals 1. So we get that the Jacobian is r. And if you might recognize this r, this not really infamous, but we've seen it before. This might be familiar from our r dr d theta. Remember when we switched from rectangular to polar? So in effect, this r comes from computing the Jacobian. Okay, the Jacobian of g of r comma theta equals x of r theta y of r theta. Okay, so that's where that came from. So good to know, right? Okay, so just another note, for these kinds of problems, for change of variables, I'll abbreviate, for change of variable problems, okay, I think that the trickiest, I'll call it like that, but I mean, it's really not that tricky. I guess it would just be it would require the most thought, like conscious thought. The trickiest part is usually just the Jacobian part. Just remembering how to calculate it. But I mean, if you do it enough times and get some practice, then it'll be pretty much routine, basically. So the trickiest part is computing Jacobian, because it is a new concept, right? So computing Jacobian. And then you would just solve like we have been. Then solve like we have been doing. Okay. And again, just to reiterate, the Jacobian, what that represents, so Jacobian of, I've just been using g, of whatever function maps one point to another in a different plane. Anyways, this represents the change in area, so change in area, in not just the area, but the change in the differential area. So the change in this thing, well, okay, I'll go back. I'll just call it area. So change in area when moving from one coordinate system to another. One coordinate system to another. So in effect, this last part here, moving from one coordinate system to another, that essentially means that you're changing variables. So changing variables, because that's the topic of this section. That's just another way to say it, right? Because you could be talking about xy coordinates, and x and y are your variables, right? And then are theta coordinates or something, and r and theta are your variables. So those are interchangeable here. But that's just important, an important connection you need to draw. And it's good to understand the meaning behind like why we're doing these calculations. Okay, so now on to a different topic, or different but related topic.
Before. Never have you had your heart on the floor. I could do it. Well, I know I could do it. Maybe